Good day everyone. Today, our group will discuss FTIR spectroscopy. Fourier transform infrared spectroscopy, also known as FTIR, is one of the most common analytical techniques used. This analytical method determines the identity of organic, polymeric, and some inorganic materials. It is called Fourier transform because it uses Fourier transform, a mathematical process, to create the spectrum from the raw data. FTIR is also used to observe the whole IR spectrum at once. The FTIR spectrometer is available as handheld portable units and as a more sophisticated unit that is typically situated in laboratories. For an FTIR spectroscopy analysis, the sample is usually positioned between the detector and the interferometer. Then, as the sample absorbs certain wavelengths, the interferogram will contain the spectrum of the source minus the spectrum of the sample. Generally, an FTIR spectrometer consists of a salt beam splitter, a moving mirror on a precision mechanical bearing, a solid-state detector, and the sufficient computing power to process the time-domain interferogram into a frequency-domain spectrum. In addition, a laser with a photodiode detector is also present for the calibration of the wavelength. Now, here are some of the advantages of using FTIR spectroscopy. In FTIR spectroscopy, compounds are analyzed quickly and accurately. Compounds analyzed can be in the form of solid, liquid, or paste. In addition, it has an improved signal-to-noise ratio at a given resolution, which is better compared to other dispersive instruments. It also has the built-in data handling capabilities, shorter scan time for all frequencies, high scan range, reduction of stray light, and it is pretty easy to clean.
Now let me discuss the principles behind Fourier transform infrared spectrometer and how does it work. In this part, I will specifically focus on the theory behind Fourier transform infrared spectroscopy, the process, the Michelson interferometer, the IR spectrum, and finally, the identification of molecule using FTIR. Matter, such as atoms or molecules, can interact with radiation. Such interaction is known as spectroscopy. In the Fourier transform infrared spectroscopy, as the name suggests, we specifically deal with the infrared region of the spectrum. The absorbing groups in the infrared region absorb within a certain wavelength region. These wavelength regions involve the near IR, mid IR, and the far IR region. The absorption peaks within this region are usually sharper when compared to the absorption peaks from the ultraviolet and visible regions. In this way, IR spectroscopy can be very sensitive in the determination of different functional groups since different functional groups absorb different particular frequency of IR radiation. Each molecule has a characteristic spectrum often referred to as the fingerprint. A molecule can be identified by comparing the absorption peaks to a different data bank spectra. IR spectroscopy can be very useful in the identification and structural analysis of a variety of substances, including both organic and inorganic compounds. It can also be used in the quantitative and qualitative analysis of complex mixtures of similar compounds. The energy possessed by infrared radiation is not enough to excite electrons. However, it is enough to cause vibrations in the chemical bonds within the molecule. These vibrations can be classified as symmetric, antisymmetric, deformation, wagging, rocking, and twisting. Just for a simple introduction regarding these vibrations, whether the stretch of a band in a molecule is asymmetric or symmetric depends on the relative movement of the atoms connected by the band. Let's take a metal group for example. If the two hydrogen atoms connected to the carbon move in the same direction during stretching, it is a symmetric stretch. If they are going in opposite directions, the stretch is asymmetric. A band vibration like stretching will only be IR active if it is accompanied by a change of dipole moment. In spectroscopy, the spectrum is being measured or determined. A source is needed to generate IR radiation. This would then be directed to the sample, where some of the light will be reflected and some will be absorbed by the sample. The light that will be transmitted, which is the one carrying the molecular information of the sample, will be sensed by the detector and converted into an electrical signal. At the center of a FTIR spectrometer is a Michelson interferometer. A Michelson interferometer produces interferent fringes by splitting beam of light so that the other beam will move to a fixed mirror and the other one to a movable mirror. When the reflected beams are brought back together, an interference pattern results. During measurement, the IR beam will enter the interferometer and is directed at the beam splitter. The beam, as the name suggests, will split. One directed at a fixed mirror and the other directed to a movable mirror. The light will then be reflected back to the beam and recombined, causing an interference which is then directed at the sample material. In this way, the spectral information of all the wavelengths is acquired simultaneously. At the end, the detector will produce a raw signal of light intensity versus the mirror position. To be able to get a sample spectrum, however, we must first acquire a spectrum without any sample to get a clean IR spectrum free from carbon dioxide and water vapor. This is called an interferogram. This will be then transformed into the classical IR plot, which is the intensity versus the wave number, yielding a single channel reference spectrum. This will then be repeated with the sample at hand, producing a single channel sample spectrum. A transmission spectrum will then be produced by combining the two by dividing the sample spectrum by the reference spectrum. This is then used to identify the chemical present in the sample. The energy needed to change the vibration of a specific chemical band is fixed. From here, the absorption of the IR spectrum for a particular molecule can be determined and can then be used to identify the bonds present in the molecule. Each of the bonds are different, thus will vibrate differently and absorb IR radiation of different wavelengths. By looking at the IR absorption spectrum, the chemical formula of a specific molecule can be determined.
Parts of a Fourier transform spectroscopy. The first one is IR source. It is made of a solid inert, heated electrically to a temperature of 1500 to 200 K. Infrared radiation is then released by the heated material. Sources used in infrared spectrometers are either Nernst Globar, or incandescent cable source. The second one is laser reference. It is overlaid to provide a benchmark to the instrument service. Typically, the spectrometer is adjusted and calibrated. The third one is beam splitter. It creates two beams of approximately the same intensity are formed. The next one is interferometer, or the two strategic mirror moving and fixated that function as interferometer. The motion of the moving mirror varies the total path length relative to the fixed mirror beam. Sample chamber. It is where the sample is placed. Then, all the characteristic wavelengths of its spectrum are absorbed, and then particular wavelengths are subtracted from the interferogram. The last one is detector. Devices that transform the electrical signal from the analog spectral output. In infrared detectors, either photon or quantum detectors or thermal detectors can be identified as the detectors used. The Fourier transform infrared spectroscopy instrument relies on interferences of different light frequencies to produce a spectrum. It has a source sample, two mirrors, a laser reference, and the detector. The energy sources hit the beam splitter and generates two beams of approximately the same strength. One beam reaches the fixed radiator. The second beam goes to the mirror. If this if these two beams meet again, they recombine and the difference in length of their direction produce an interferogram which is positive and destructive.
Now, the setup of an FTIR spectrometer will be discussed. First, we will tackle about how the sample is introduced to the instrument. And second, how does the FTIR spectrometer produces the spectrum of the sample. First is the sample introduction. An FTIR spectrometer can investigate various types of samples. It's one of its advantages compared to other infrared spectrometers. It can investigate solids, liquids, and even samples that are in powder or paste form. Shown here is an schematic diagram of the sample introduction. To introduce a sample, we need an infrared source, an ATR crystal, and a detector. But before we go through this process, let's talk about how important an ATR crystal is during sample introduction. Generally, there is a long list of ATR crystals that we can use on experiments involving the FTIR spectrometer. But listed here are the most widely used ATR crystals, and these are the monolithic diamond, germanium, and the zinc selenide. Now the data here provided for each of the crystal, their spectral ranges, and the refractive indices are very important because it dictates what type of ATR crystal we can use depending on the sample we are investigating. Because the refractive index of the ATR crystal should be greater or higher than the sample in order for the spectrometer to read measurements. So for example, we are investigating a sample that has a refractive index of 3. So we need to use an ATR crystal that has higher refractive index. In this case, we can use germanium. Spectral data is collected during sample introduction because the infrared light from a source interacts with the sample matter. To collect a spectra, we need an IR light from an appropriate source which will be directed to the sample, placed above and in a close contact with an ATR crystal. As the light passes through the ATR crystal, some of the light will be internally reflected and some will be partially absorbed by the sample. But still a large fraction of the light will be transmitted to the detector, and this fraction of light actually carries the molecular information of the sample. Next is the instrumental setup. We have here the schematic diagram of an FTIR spectrometer. We can observe that a large portion of the instrument consists the Michelson interferometer, which is actually a core component of FTIR spectrometers and makes the instrument distinguishable from any other classical spectrometers. We also have an IR source, the sample, placed in a sample compartment containing the ATR crystal, and the detector connected to a computer. Also, please take note of a very important step in FTIR spectroscopy, which is the Fourier transform, already mentioned in the earlier parts of this report. During the experiment, the infrared light will enter the interferometer and hits the beam splitter. The beam splitter will split the light into two beams and sends them into different directions at an angle of 90 degrees. Now, once they meet again and recombine in the beam splitter, constructive and destructive interferences will occur, leading to the creation of an interferogram. The recombined beam now passes through the sample, and the sample will absorb all of its characteristic wavelengths while also subtracting the specific wavelengths indicated in the interferogram. Then the detector will report simultaneously a plot of energy variation versus time of all the specific wavelengths it detects. As I've mentioned, the detector reports a time domain spectrum. That is a plot of energy variation in voltage versus time, like this one. But note that time domain spectrums are difficult to interpret for either qualitative or quantitative analysis. That's why we need to convert a time domain spectrum into a frequency domain one. This is where the Fourier transform comes in because it allows us to convert a time domain spectrum into a frequency domain spectrum, like this one. This is what a frequency domain spectrum looks like. This is a plot of intensity against wave numbers. Notice that it is easier to interpret this kind of a spectrum compared to the time domain spectrum. Finally, I will discuss experimental setups involving the FTIR spectrometer. We can see here that labeled number 1 is the sample. I've mentioned earlier that various types of samples can be investigated by an FTIR spectrometer. Labeled number 2 is where the ATR crystal is located, and surrounding it is the sampling surface. Now the anvil is used to put pressure on solid samples because it is important for the sample and the ATR crystal to have a very close contact. And then lastly, the computer. This is where the frequency domain spectrum will be displayed.
Okay, before every measurement, calibrating the instrument is necessary in order for it to give results that are accurate. For FTIR, the first step in the calibration is sample preparation. When using transmittance method, a solid sample was prepared by creating a disk with a standard, and the most often used standard is potassium bromide because this salt is optically transparent in the IR region. Only a small amount of the sample was needed in creating a disc. That's about 2 mg of the sample, and in every 150 or 200 mg of potassium bromide. This mixture was mixed and ground uniformly, and in a pellet set, a pinch of this mixture was placed. The pellet set was squeezed with a press, and this creates a disc of potassium bromide with the sample in it. Here in the photo is an example of a potassium bromide pellet. Now, for liquids, a viscous sample, or a sample that has a high boiling point, was placed between two potassium bromide or sodium chloride glass plates, like these sodium chloride plates in the photo. And these plates must not be cleansed with water because they are made of salts, so they can permanently be damaged by water. Not even the moisture from our hands must have contact with the middle part of these plates. So, in preparing liquid samples, the plates were cleaned with dichloromethane first, then a small amount of the sample was dropped between them. The application of sample was done in a sample holder, and this holder also secured the plates. For a volatile sample, it was first mixed with carbon disulfide or carbon tetrachloride into a 10% sample solution before it was placed inside the glass plates. Now, for gases, a gas cell, as in the image shown, was used. This cell has potassium bromide windows on each end. The cell was first vacuumed to remove any molecule present inside before inserting the gas sample inside the cell. The potassium bromide ends must not be touched with bare hands because they are fragile. The second step in calibration is performing a background scan, because when a sample spectrum is measured, there are other signals from the environment and the instrument itself that are measured along with the signal needed. A background spectrum compensates for this added signal. This spectrum was measured by scanning a blank, which were the disk, the glass plates, or the vacuumed gas cell, depending on the sample. They are measured without the presence of the sample. The instrument automatically subtracted the background spectrum from the scans that followed. The photo shown here is a background spectrum. So if the resulting background scan was not similar to this, then the instrument or the disk, glass plate, or gas cell must be cleaned again. Now, there is another method for FTIR, which is the attenuated total reflectance. In this method, there is a crystal on the sample platform and the pressure anvil built into the device. The sample can be scanned here as it is without any preparation like that of the transmittance method. The platform and the anvil was cleaned with a tissue paper wet with the ionized water or alcohol, and a background scan was measured with nothing on the platform. When the background spectrum was stored, the sample was measured. By this time, the sample was already inside the sample holder for solid and liquid, or in the gas cell for gas sample. There is a compartment in the instrument where the sample holder was placed. The door of the compartment was closed and the spectrum of the sample was measured. Now in this photo, a sample holder with a sample in potassium bromide plates was held secure in the FTIR instrument. Now in ATR method, a pinch or drop of the sample was placed directly on top of the crystal, and the pressure anvil was let down until a clicking sound was heard. This pressure anvil was used to make the contact of the sample to the crystal firm. After setting up the sample in the instrument, the spectrum was scanned and measured.
Application of FTIR. The total scope of FTIR applications is extensive. Some of the more common applications are quality verification of outgoing or incoming materials, reformulation of polymers, rubbers, and other materials through thermogravimetric infrared or gas chromatography infrared analysis, microanalysis of small sections of materials to identify contaminants, analysis of thin films and coatings, monitoring of automotive and smokestack emissions, and failure of analysis. Infrared spectroscopy is an important technique in testing, analyzing, and monitoring the quality of air, water, and soil to focus on the environmental and health problem caused by decreasing pollutions. It is also used as a technique for rapid determination of trans fat content of manufactured food products. The technique offers a green method of testing and fast, accurate results with the added benefit of saving money on the cost of consumables and is instrumental for in compliance with food labeling requirements and to help promote healthy eating living. It is also a technique that helps to build a complete understanding of evidence samples and allow forensic scientists to confidently give expert testimony in court. These techniques can provide fast, easy, and consistent analysis for seized drugs, controlled substance and cutting agents, clandestine labs, chemical evaluation, hit-and-run paint and materials, textile identification, fibers, coatings, and residues. In pharmaceutical laboratories, FTIR is an excellent technique for analysis due to its easy to use, sensitive, fast, and helps ensure regulatory compliance through validation protocols. Applications include basic drug research and structural elucidation, formulation development and validation, quality control process for incoming and outgoing materials, and packaging testing. FTIR spectroscopy is used to identify compounds such as compounded plastics, blends, fillers, paints, rubbers, coatings, resins, and adhesive quickly and definitively. It can be applied across all phases of product life cycle, including design, manufacture, and failure analysis. This makes it a useful tool for scientists and engineers involved in product development, quality control, and problem solving. Other FTIR applications: opaque or cloudy samples, energy-limiting accessories such as diffusive reflectance or FTIR microscopes, high-resolution experiments as high as 0.001 cm -1 resolution, trace analysis of raw materials or finished products, depth profiling and microscopic mapping of samples, kinetics reaction on the microsecond timescale, analysis of chromatographic and thermogravimetric sample